All right, we are going to look at nuclear physics, the very, very basics. So, what are we looking at here? So, we have the model of an atom, and in an atom, we have some protons, and then we're going to have some neutrons. So, we're going to say these are my protons. And then the other things found in the nucleus of the atoms are neutrons. And then going around the outside are electrons. There we go. It never changes color fast anymore. So if I was looking at this, then I would know, and let's say I don't know what this element is. This is some mystery element. So without putting the symbol, what do I know? Well, I know it has an atomic number, which is the number of protons, 1, 2, 3, 4, 5, 5. And it has an atomic mass. So atomic number. And these are things that we see on a periodic table, right? Atomic number, which is the number of protons. And then the one up top is the atomic mass. So 1, 2, 3, 4, 5. So this would be 10 atomic mass. So this isn't nuclear physics. This is just understanding the symbol and what the information it gives us, right? Which is protons plus neutrons. So there we go. Now, in nuclear physics, what we're saying is there is an unstable nucleus. The nucleus has too much energy. The protons and neutrons are moving around too fast, and the bonds that are holding them together, or the forces that are holding them together, are just not strong enough, and they're going to start to break apart. The nucleus is going to start to break apart. Now, it can do this a few different ways. It can just go through fission and explode, like in a nuclear reactor or a nuclear bomb, and just breaks apart to many pieces. The other thing that it can do is it can just give off pieces, and it gives off a few pieces. It can stabilize itself, right? It gets smaller, stabilizes itself, and then it's okay after that point, right? And some of them go through many things, right? It's unstable, so it gives off a piece, turns into something else, and it gives off another piece, turns into something else, gives off another piece, right? So it just keeps going through this process where it keeps breaking, slowly over time. So a lot of different things can happen to the nucleus of an atom if it's unstable, right? It can explode and break up, just break up once and just break up in a bunch of pieces. It can just give off one thing and be happy, or it could just keep over time giving off more and more pieces and just take a long time to get unstable. That's radiation, right? Things are leaving the nucleus of the atom. They're getting ejected. So there's a few things that tend to be how the nucleus breaks up. If we have a nucleus that's unstable and it's giving away some mass to stabilize itself, then it tends to give it off in specific ways, right? The first thing that it can give off is what we call an alpha particle. Alpha particle looks like this. Alpha particle. And an alpha particle tends to have an atomic mass of 4, so 2 protons and 2 neutrons, atomic number of 2. So really, if I start with that, alpha particle has atomic number of 2, so it has 2 protons, atomic mass of 4, so it must be 2 protons, 2 neutrons, right? And that is something that could be ejected out of the nucleus of the atom. Another thing that could be ejected out of the nucleus of an atom is a beta positive particle, which is essentially something that has a charge of 1, but it doesn't really have mass. So it's a lot like an electron. It's what we call a positron. So it has a charge of 1, but it has no mass. And we call that a positron. And it's a lot like an electron because protons and neutrons are big. Electrons are small. They essentially have no mass. Beta negative. Beta negative, there we go. Well, beta negative is an electron, so amazingly enough, an electron could be ejected out of the nucleus of an atom. When an electron has a charge of -1, still has no mass, So that's the way we write it, right? So this one is just like everything we saw in the periodic table. These are, and I wouldn't say uniquely, but we're dealing with unique objects. So we have to figure out how to fit that into our standard atomic mass, atomic number. Whereas a charge of 1 has a mass of nothing because it's very, very small. This one has a charge of -1, has a mass of nothing because it's very, very small. All right, the last one is a photon. I'll write it up top. And a photon is basically just energy, right? It doesn't actually give away anything with charge, doesn't give away anything with mass. It just gives away energy. And a photon looks like an alpha particle on its side, and it doesn't have a charge because it's just energy and it doesn't have mass, right? So photons, light is a form of a photon, or photons can be what light is. So photon decay is when it just gives away energy. It doesn't give away any pieces or anything like that. It just gives away some energy, so it has less energy. So these are the 4 things that tend to be what is given away from a nucleus of an atom when it's unstable, right? The other option, like I say, is to go through fission and just basically blow up. And then, yeah, then it's really percentages, what it blows up into, what pieces tend to be made more often, what pieces tend to be made less often. So let's look at the next part. Let's say I have something. I don't even care what it is. So let's say I have something. And you know what? I guess I will look up something just so I have it. But let's say I have bismuth, and it's 83. And let's say I have one that's unstable and has an atomic mass of 212. Now, there's a lot of different forms of bismuth, right? This is not, if we look at the periodic table, it doesn't list 212, right? But 212 is an uncommon one, but it has 83 protons, and if I subtract 83 from 211, I know how many neutrons they have, right? And it's not common in nature, which means it's probably an unstable one. It's going to decay into something else. So let's say it does that. Let's say it goes through alpha decay. Well, if it goes through alpha decay, then I know one of the things it produced is an alpha particle. That's what left the nucleus of the atom. Well, then what did it turn into? Well, if 2 protons left, and that means there's 81 left. If 4 protons and neutrons in total left, it's got to be 208. So when it went through this decay, it turned into whatever this is. Right? But it turned into the element that has 81 protons and an atomic mass of 208. Now, I'm not saying it naturally does that. I don't know what this decays into. We could look it up. But let's say that it goes through beta positive decay. So it gives off a proton. Well, a proton has an atomic number of 1. It essentially has no mass. So what did this one turn into? Well, it keeps the same atomic mass, but one of the protons turned into a neutron. So this one, after it goes through decay, will turn into, I know this one's lead. So it turned into lead 212 if it went through beta positive decay. We could do it with the other one. The math is fairly straightforward, right? Let's say that this went through beta negative decay. Well, then an electron left, which has an atomic number of -1, still no mass. So it's still going to be 212. But now it's going to be what? Well, this has got to be 84, which essentially means a neutron turned into a proton, which are things that could happen. And then I believe that's polonium. So I'm just looking and saying, okay, I know this. So what does this have to be? So they still add up to these numbers. Again, I know this. What does this have to be? So it turns into these numbers, right? I'm just balancing them out. And if this went through photon radiation, or sometimes it's called gamma radiation. So I guess I should put that too. The other name is gamma radiation. So if it went through that, well, then it gets rid of a photon, which is 0, 0, right? No mass, no charge. Well, then what is it? Well, it's still bismuth 212. It just has a slightly less energy in the nucleus. So these are the ways that it could do it. You simply just look at it, right? If I gave you this and this, you'd be able to tell me the particle. If I gave you this and the particle left, you could tell me what it was. So we could balance equations this way just by understanding the 4 different major types of decay. Now, if we want to look at how dangerous this is or how much energy is getting, that really comes back to energy, right? If this is a radioactive decay or a nuclear decay that is dangerous, it's because it's giving off a lot of energy, right? when this beta particle, this positron here is ejected, if it's ejected with a lot of energy, well, this is a dangerous thing. If it's ejected with a small amount of energy, it's not a dangerous thing. And let me back up a little. When I say that, right, if only one positron's made, well, that's never dangerous, right? We need billions of them, right? But again, think about chemistry and think about how many atoms make up a gram of material. It's an enormous number, right? So if we're getting a lot of them to go through decay, we're giving off enormous amounts of positrons or electrons or photons or alpha particles, right? Kind of depends on what it is. But the energy that they're ejected absolutely matters. So how do we get that? Well, this is the equation that everyone knows and no one knows what it means, right? E equals mc squared. So this is based on the premise of we could have mass and we could turn mass into energy, right? So it violates two major laws, but it's still right. First of all, it violates conservation of energy because now we're saying, hey, we can make energy. We could take mass and turn it into energy, so we can make energy. Or vice versa, we could take energy and turn it into mass. So it's violating conservation of energy. And back in chemistry class, it's violating conservation of mass, right? We always say that, well, mass doesn't change. It may change forms, but we still have the same amount of matter as before. Well, no, this is telling us, hey, we could turn mass into energy. So, kind of the foundation of physics gets violated and kind of the foundation of chemistry gets violated, right? Where now we really have to say that it's not conservation of mass or conservation of energy, it's conservation of energy and mass, right? The two things together. They can turn from one to the other, but that's it, right? That's about the only thing we can do. Now, to be honest with you, the fact that this violates those things doesn't matter so much because we're talking about very specific cases where this happens. Mass does not turn into energy all day, all the time, right? It's not a common thing. But what does that mean? Well, if I looked at one of these, and let's just say that I look at this one. So let me do this slightly different. There we go. So let's say I look at this one, just that top one. Get rid of all this. And if I look this up, I can get a mass for this. So this has a certain amount of mass. Call it mass 1. This has a certain amount of mass. I'm going to call this mass 2. And this has a certain amount of mass. And I'm going to call this mass 3. There we go. Right? So I have one big object and I break it up into two pieces. And each piece has its own mass and this individual has its own mass. But it's telling us, though, if we look at this, the mass of this will not equal the mass of these two added together. There will be a difference in mass, which means either mass was lost or mass was gained, right? So if I go back to this, E equals mc squared, then it is the idea that we could turn mass into energy. So if this mass is greater than these two masses, then that means that mass was lost. Whatever mass was lost, we take that mass that disappeared, multiply it by the speed of light squared. That's how much energy was produced in the process of breaking this nucleus apart. It's as simple as that, right? So we figure out how much mass was lost. If it's the other way around, and this mass is actually smaller, and these two add up to a mass that's greater, well, then that tells me something. That tells me that, hey, we created mass, which means the system had to lose energy. So in nuclear decay, in these things that we're talking about, we know that this is an unstable atom that has extra energy, right? And then it explodes and it breaks up into these pieces. So we know that it's this case. We know that mass is lost and energy is created because it gave away energy in the process of breaking up, right? So the energy that it had, right, it now gives away some of that energy. So anything that's going through nuclear decay, this side, the total mass is going to be more than the sum of the individual masses. That's what's going to happen, right? The second case is when we have something like fusion, where we're putting pieces together and making something bigger. And in order to do that, we have to give it some energy to make it happen. So this isn't radioactive decay. Is it a possibility out there in the world? Of course it is, right? We can take particles, give them some energy, and then let them combine or fuse together, which is nuclear fusion. But that's essentially it. If I know how much mass this has, I know how much mass this has, I know how much mass this has, I figure out the difference between the total mass. What is this mass before it broke apart? What's the new mass of the pieces added together after it broke apart? That difference in mass, that loss of mass, we multiply it by the speed of light squared, and we have the energy that this creates. So let's say we have one, and let's say we have, and I'm not going to look up actual ones. Let's say we have some mystery element, right? And that mystery element, let's say we went somewhere else, we have this mystery element, and it has an atomic number of 94, and it has atomic mass of 200. And actually, I guess I'll look it up, just so we're using the real one. So that would make this, there we go, that would make this. And let's say it goes through alpha decay. So it's going to give away an alpha particle. And therefore, what's left after that has got to be 92 and 196, which makes it uranium. So that one I know, uranium. So this would be an example of alpha decay. Now, if I look these up, I can now get the atomic masses of these things. Now, you would be supplied these, or you'd be given a way to look them up. Right. And because I'm making this up, I don't know if this one actually exists, so I'm just gonna write down. So let's say that this has an atomic mass of 200.56 atomic mass units, and we'll see what that is in a second. And let's say that this has an atomic mass of 195.4 atomic mass units. And let's say that the alpha particle, which really does have a mass, so we'll get that one real quick. Now, that is a real one, so we'll use the real number for that. That works out to be 4.0015 atomic mass units. So let's carry these out. We'll say that's that, and we'll say that's that. So these are our atomic masses. Well, when I add these two together, sorry, that's 4, because it's close to 4. Right? So they're all really close to the atomic mass numbers, but the actual mass is slightly different. Some are a little more, some are a little less. So this is 200.56 atomic mass units, which we'll deal with in a second. And then it's 195.4, and this is 4.0015. So let's add those together. 195.4 plus 4.0015 works out to be 199.4015. So that means there's a loss. If I take this and subtract this, there is a mass lost of 1.15851585 atomic mass units. Now, I'm hoping you understand the concept here, because we're really just finding how much mass was lost and multiplying it in the equation. And we're pretty much done. E equals mc delta t. I'm sorry, E equals mc squared. I'm on a completely different equation. E equals mc squared. We have to put a conversion in there. So this is the amount of mass that was turned into energy. And this is in atomic mass units. But we have a conversion. And how many atomic mass units are in a kilogram? Works out to be 1 atomic mass unit is 1.6605 times 10 to the 27 kilograms. So I'm doing that. Converting it to kilograms, which is good because I'm going to want my answer in joules. And then the speed of light squared, which is 3 times 10 to the 8th meters per second squared. So I'm going to take that number, multiply 1.6605. I'm going to multiply it by 3 times 10 to the 8th squared, and I will have my answer. Works out to be 1.73 times 10 to the negative 10 joules of energy. So during this process where this breaks apart into these two pieces, this is how much energy is created. And really more specifically, it's kinetic energy, because what are these two pieces going to do? They're going to, I don't want to say necessarily explode, but they're going to break apart, and they're both going to go flying in different directions, right? Because they have to satisfy conservation momentum, which we didn't even look at here, right? But conservation momentum is satisfied. Newton's laws are satisfied. Everything has to be satisfied when these two pieces break apart. So they have to move away from each other, and they move away from each other in very specific ways. And this is how much kinetic energy is created so that they'll move away from each other. And that's it. The very basics of nuclear physics.